Tonight, we're going to travel farther and farther from Earth, crossing the invisible boundaries where spaceflight slowly becomes something much more dangerous. Close to home, astronauts still have layers of protection around them. The International Space Station remains inside much of Earth's magnetic shelter. Mission control can answer within a fraction of a second. Replacement parts can arrive aboard a cargo spacecraft, and an emergency return vehicle is already waiting at the station. But those protections begin disappearing almost as soon as the journey outward begins. Beyond Earth's magnetic field, radiation reaches the spacecraft with far less resistance. Near Mars, a message from home can take more than 20 minutes to arrive. Past Jupiter, sunlight falls to roughly 1/27th of its strength near Earth. At the distance of Voyager 1, a command takes nearly a full day to cross the darkness in only one direction. The horror arrives one loss at a time. A broken pump near Earth may be a maintenance problem. On the way to Mars, it could become a mission-threatening emergency. Between the stars, the same failure could happen years before anyone on Earth even receives the message describing it. Every kilometer outward removes another safety net. Fast communication disappears. Rescue becomes impossible. Medical help becomes a set of instructions arriving too late. Power grows harder to produce. Machines must survive longer without replacement, and eventually, turning around may require more energy than the spacecraft has left. By the end of tonight, you're going to understand what a traveler would lose at every major boundary, where the final practical connections to Earth begin to disappear, and why space becomes more horrifying the farther you travel. Before we move beyond orbit, take a moment to like the video and subscribe if you enjoy calm explorations of the universe. It helps this channel continue making long journeys like this one. The best place to begin is only about 400 kilometers above us. At that height, the International Space Station travels at roughly 27,600 kilometers per hour. It completes one orbit in about 90 minutes, carrying its crew around Earth approximately 16 times each day. The station moves through vacuum at a speed that would cross an entire country in minutes. Yet in practical terms, it remains close to home. Radio signals cover the distance between the station and the ground almost instantly. Flight controllers can watch the condition of its electrical system, cooling equipment, atmosphere, computers, and orbit as those systems change. When an alarm appears, specialists on Earth can examine data, compare it with years of engineering records, and help the crew work through the problem. The astronauts are performing the repair, but they are rarely solving it alone. That support reaches beyond advice. Cargo vehicles regularly carry food, clothing, scientific equipment, filters, gases, and replacement hardware into orbit. A failed component does not always need to be repaired forever. It may only need to remain usable until another spacecraft arrives with a new one. The station can survive certain losses because a supply chain still connects it to factories, laboratories, and warehouses on the surface. A return path is also kept beside the crew. A human-rated spacecraft remains docked with enough seats for the people aboard. If the station develops a serious pressure leak, fire, collision risk, or another emergency that makes continued habitation unsafe, the crew does not need to wait for a rescue mission to launch. Their vehicle home is already attached. None of this makes low Earth orbit harmless. The station depends on a large collection of pumps, valves, fans, batteries, computers, solar arrays, radiators, pressure seals, and life support equipment. Small fragments of orbital debris can threaten its hull. Radiation exposure is higher than it is on the ground. A fire inside a sealed spacecraft remains extremely dangerous, and every return through the atmosphere carries risk. What changes the outcome is the amount of help surrounding those dangers. A cooling pump can be monitored by engineers who help design it. A blocked filter can be replaced from onboard stores or added to a future cargo manifest. A sick crew member can speak with doctors without waiting several minutes for each sentence to cross space. If the entire station becomes unsafe, Earth is hours away rather than months or years. That makes the International Space Station the last safe orbit in a very specific sense. It is the farthest place where humans have lived continuously, but it still functions as part of an Earth-based system. The station is the visible outpost. The larger machine includes tracking antennas, launch sites, cargo vehicles, mission control rooms, medical teams, manufacturers, and thousands of people who never leave the ground. And even that enormous human network explains only part of the protection. The station also remains inside a much older system, created by the planet long before spacecraft existed. It surrounds Earth, bends the paths of charged particles, and reaches far beyond the atmosphere below. Before the journey can move outward, we need to understand the invisible shield the astronauts have not fully left behind. Most of that planetary protection begins far below the station, in the layers of air spread between orbit and the ground. The International Space Station circles Earth at an altitude of roughly 400 kilometers inside a region called the thermosphere. A trace of atmosphere still exists there. It is thin enough that the station experiences near vacuum, yet dense enough to create a small amount of drag that gradually lowers its orbit. Periodic engine burns are needed to raise the station again. Almost all of the atmosphere lies below it. Those gases perform several forms of protection before radiation can reach the surface. Ozone absorbs much of the ultraviolet light that can damage living tissue. Oxygen and nitrogen stop X-rays high above the ground. Incoming atomic nuclei collide with air molecules and break into showers of smaller particles, leaving the atmosphere to absorb much of their energy before they reach sea level. The station has already moved above most of that material. Its aluminium walls and internal equipment provide some shielding, but the crew no longer has kilometers of air overhead. Another part of Earth's protection still surrounds them. Deep below the surface, liquid iron moves through Earth's outer core. This electrically conducting fluid circulates as heat escapes from the planet's interior. Earth's rotation helps organize that motion, creating a planetary magnetic field through a process called the geodynamo. That field reaches thousands of kilometers into space. Charged particles respond to it because moving electric charges curve as they cross magnetic field lines. A slower particle may be turned aside or guided along the field. A very energetic particle can pass through with less deflection. The result depends on its speed, electrical charge, direction of travel, and the strength of the field at that location. The region controlled by Earth's field is called the magnetosphere. Its shape is constantly altered by the solar wind, a stream of charged particles flowing outward from our star. On the side facing that flow, the magnetosphere is compressed to roughly 60,000 kilometers from Earth under typical conditions. Behind the planet, it stretches into a magnetotail that can extend more than 1 million kilometers into space. Auroras reveal part of this process. Electrons and protons guided toward the polar regions collide with oxygen and nitrogen in the upper atmosphere. Oxygen commonly produces green or red light, while nitrogen can add blue and violet. The glowing curtains seen over northern Canada, Alaska, Scandinavia, and Antarctica are visible evidence that charged particles are being directed by Earth's magnetic field. The protection is uneven. Earth's magnetic axis is tilted and offset from the planet's center, and the field is weaker over part of the South Atlantic. This creates the South Atlantic anomaly, a broad region extending over parts of South America and the Atlantic Ocean where trapped radiation reaches unusually low altitudes. The station's orbit is inclined by 51.6 degrees, carrying it through this region repeatedly. Astronauts receive a measurable increase in radiation while passing through it. Sensitive instruments aboard satellites are sometimes switched off or placed in protective modes because energetic particles can produce false readings, damage detector pixels, or flip information stored inside computer memory. Altitude also matters. A satellite farther from Earth can spend more time among trapped particles. Latitude changes how strongly the field guides particles toward a spacecraft. Solar activity can expand, compress, or disturb parts of the magnetosphere. Particle energy determines whether the field bends a path significantly or allows the particle to penetrate much farther. For these reasons, remaining inside the magnetosphere does not make low Earth orbit radiation free. A 6-month station mission can expose an astronaut to roughly 80 to 160 millisieverts, depending on conditions and shielding. Average natural background exposure at Earth's surface is only a few millisieverts per year. The difference remains substantial. Earth's atmosphere and magnetic field reduce the amount and type of radiation reaching the station, while the planet's nearby infrastructure helps crews manage what remains. The astronauts have risen far above the surface while staying within the physical reach of their world. Continuing outward carries them through regions where Earth's magnetic field has trapped energetic particles for long periods. Those regions form the Van Allen belts, the first major radiation environment an outbound crew must deliberately cross. The first spacecraft to reveal these trapped particles was Explorer 1, the first satellite launched by the United States. It lifted off from Cape Canaveral on January 31, 1958, carrying a radiation detector developed by a team led by physicist James Van Allen. The instrument was designed to count energetic particles. During parts of the orbit, however, it reported almost nothing. Researchers initially suspected a malfunction. The detector had actually entered regions where radiation was so intense that the instrument became overwhelmed and temporarily stopped producing useful counts. Later missions confirmed that Earth is surrounded by broad zones of trapped charged particles. They became known as the Van Allen radiation belts. The inner belt begins several hundred kilometers above parts of Earth and extends outward for thousands of kilometers. It contains many energetic protons, including particles produced when cosmic rays strike the upper atmosphere and create unstable neutrons. Some of those neutrons decay into protons that become trapped by Earth's magnetic field. The outer belt lies farther away and contains large populations of high-energy electrons. Its size can change considerably during geomagnetic storms, when activity from the Sun disturbs Earth's magnetic environment. At times, the outer belt can swell, weaken, split into separate regions, or temporarily gain an additional layer. These belts have no solid surface. Their radiation levels vary with altitude, latitude, particle energy, and current space weather. A spacecraft can pass through a relatively mild region, while another route, taken at another time, produces a much larger dose. That variation shaped the Apollo flight paths. The crews did not travel straight through the most intense parts of the belts. Mission planners selected trajectories that crossed thinner regions, and the spacecraft moved through them within a few hours. Radiation dose depends partly on intensity and partly on time. Spending several minutes in an elevated radiation field produces a smaller accumulated dose than remaining there for days. Shielding inside the command module reduced exposure further, while continuous monitoring of solar activity helped mission teams avoid launching into known severe conditions. The Apollo astronauts therefore crossed the belts without receiving immediately dangerous doses. Their journeys showed that the belts are a serious engineering constraint, rather than an impassable barrier. More than 50 years later, Artemis I carried a much larger collection of radiation instruments during its uncrewed flight around the Moon in 2022. Sensors were distributed throughout the Orion capsule to measure how radiation changed from one location to another. Two human-shaped experimental torsos traveled in passenger seats. They were named Helga and Zohar. Each represented an adult female body and contained materials designed to imitate human tissue, bones, and organs. Thousands of small detectors were placed inside them. Zohar wore a protective astrorad vest, while Helga traveled without one. Comparing their measurements allowed researchers to study how much protection the vest offered to radiation-sensitive organs. Orion also carries a practical shelter strategy for solar storms. During a major particle event, astronauts can move into the lower central part of the cabin and arrange food, water, equipment bags, and other stored material around themselves. These supplies already have to be carried, allowing their mass to serve temporarily as additional shielding. The first crewed test of Orion beyond low Earth orbit followed in April of 2026. Artemis II launched on April 1st with 4 astronauts aboard. The mission traveled around the Moon and returned to Earth on April 10th after nearly 10 days in space. At its farthest point, the crew reached 248,655 miles from Earth, setting a new distance record for human travel and passing the record associated with Apollo 13. Throughout the mission, detectors measured the radiation reaching different parts of the cabin and the doses received by the crew. The flight added modern human data to results gathered by Apollo, Artemis I, and decades of robotic missions. The radiation belts can be crossed because the route is chosen carefully. The spacecraft provides shielding, and the time inside the strongest regions remains limited. Every part of that protection depends on planning before departure. Beyond the belts, the crew can no longer reduce exposure by completing the crossing within a few hours. The Moon keeps them outside most of Earth's magnetic shelter for days, while the nearest replacement part remains hundreds of thousands of kilometers away. At the Moon, distance begins changing what help can accomplish. The average separation between Earth and the Moon is about 384,400 kilometers. Because the Moon follows a slightly stretched orbit, that distance varies by tens of thousands of kilometers during each month. A radio signal usually takes about 1.3 seconds to travel from one world to the other. That delay is noticeable during conversation. A person may begin replying before hearing the end of the previous sentence. Even so, engineers on Earth can still follow an unfolding problem almost as it happens. Instrument readings arrive within seconds. Calculations can be checked quickly, and new instructions can be transmitted while the situation is still developing. Physical assistance moves at a very different speed. A spacecraft traveling between Earth and the Moon needs several days to complete the journey. No replacement vehicle could reach a lunar crew during the first minutes or hours of a serious emergency. The importance of that difference became clear during Apollo 13. The mission launched from Florida on April 11, 1970, carrying Jim Lovell, Jack Swigert, and Fred Hayes. Their destination was the Fra Mauro Highlands on the Moon. About 56 hours after launch, while the spacecraft was more than 300,000 kilometers from Earth, an oxygen tank inside the service module failed. The accident damaged the second oxygen tank and caused oxygen to escape into space. The command module depended on those tanks for breathable oxygen and for the fuel cells that generated electricity and water. As pressure readings fell, the planned lunar landing ended, and the spacecraft became a survival system with a rapidly shrinking supply of power. The crew shut down most of the command module to preserve its batteries for re-entry. They moved into the lunar module Aquarius, which had been designed to carry 2 astronauts from lunar orbit to the surface and back. It now had to support 3 people during the journey around the Moon and home. Aquarius had been intended to sustain 2 astronauts for roughly 2 days. It supported 3 astronauts for close to 4 days. That extra person changed the atmosphere inside the cabin. Lithium hydroxide canisters removed carbon dioxide from the air, but the lunar module used round canisters, while replacement canisters from the command module were square. Rising carbon dioxide could eventually cause headaches, confusion, unconsciousness, and death. Engineers in Houston gathered materials available aboard the spacecraft and assembled a working adapter on the ground. Their design used items such as plastic bags, cardboard, a suit hose, and tape. The crew followed the transmitted instructions and built the same device inside Aquarius, allowing the command module's square canisters to work with the lunar module's system. Earth supplied the procedure within minutes. Every physical object used in the repair had already crossed the distance with the crew. Trajectory created a second challenge. Apollo 13 had begun its journey on a path that could naturally loop around the Moon and return toward Earth. Before the accident, a planned maneuver had shifted the spacecraft away from that simple free return route to support the intended landing at Fra Mauro. Mission controllers calculated new engine burns to restore a safe path. The lunar module's descent engine, originally meant to lower Aquarius toward the Moon, was used to alter the course of the entire connected spacecraft. After passing behind the Moon, another burn shortened the return journey and adjusted the landing point on Earth. Each calculation depended on the engine producing the expected thrust. The guidance system had to remain usable, and the crew had to orient the spacecraft correctly while conserving electricity. Water became tightly rationed. Cabin temperatures dropped as equipment was switched off. Moisture condensed on the cold interior surfaces. Mission control remained closely involved throughout the crisis. Specialists calculated power-up procedures, checked consumable levels, tested repairs, and prepared the command module for re-entry. The crew heard their voices with only a brief pause. Those voices could guide the astronauts through equipment they already possessed. They could not deliver another oxygen tank, another battery, or another engine. Apollo 13 returned safely on April 17, 1970, after traveling around the Moon without landing. Its survival showed how much can still be accomplished when communication remains nearly immediate and a workable route home still exists. Near Mars, the same radio exchange stretches from seconds into minutes. An emergency can change completely before Earth even receives the first description of what happened. Mars never remains at one fixed distance from Earth. Both planets travel around the Sun at different speeds, following separate orbits that bring them closer together and then carry them far apart again. Earth completes one orbit in about 365 days. Mars needs roughly 687. At their closest favorable approaches, the planets may be separated by less than 60 million kilometers. When they occupy opposite sides of their orbits, the gap can grow beyond 400 million kilometers. Radio waves travel at the speed of light, close to 300,000 kilometers per second. Even at that speed, a message usually needs somewhere between about 3 and 22 minutes to travel from Earth to Mars. A question sent during the longest delays may not receive an answer for roughly 44 minutes. That limit comes from distance itself. A larger antenna can collect a weaker signal. More transmitter power can improve reception, while better compression can place more information into the transmission. None of those improvements can make the signal arrive sooner than light allows. Robotic missions already operate around this delay. Perseverance landed inside Jezero crater on February 18, 2021. Its controllers at NASA's Jet Propulsion Laboratory do not steer it continuously with a joystick. The rover's position, images, and engineering data first travel from Mars to Earth. Scientists and engineers then study the terrain, choose targets, prepare commands, and send a plan back across interplanetary space. A transmitted plan may tell Perseverance where to drive, which rock to examine, and when to operate an instrument. Onboard computers handle the immediate details. Cameras observe the ground ahead, and autonomous navigation software identifies rocks, slopes, or other hazards that the rover should avoid. This independence allows Perseverance to travel farther during a Martian day than earlier rovers could manage under more cautious command methods. It also reflects a basic fact of Mars exploration. The rover cannot stop beside every stone and wait for a human decision. Landing requires much greater autonomy. When Perseverance reached Mars, it entered the atmosphere at close to 19,500 kilometers per hour. Over approximately 7 minutes, it had to slow through atmospheric drag, deploy a parachute, discard its heat shield, measure the ground below, select a safe landing area, and descend beneath a rocket-powered platform. During the final stage, the platform lowered the rover on cables in a maneuver known as the sky crane. Perseverance touched the ground, the cables were cut, and the descent stage flew away to crash at a safe distance. Every important decision occurred on board. Mars was more than 11 light minutes from Earth at the time. By the moment Mission Control received confirmation that atmospheric entry had begun, the rover had already landed successfully or had been lost. Human crews would experience the same delay during much less predictable events. A pressure sensor might report a cabin leak. Smoke could appear behind an equipment panel. A crew member could suffer a serious injury while another astronaut is outside the habitat. Electrical power might fail during a dust storm when solar generation is already reduced. The first response would come from the people present. They would isolate damaged equipment, identify the source of the problem, and decide which systems could be shut down safely. Earth-based specialists could study the transmitted data and offer detailed advice later, but their guidance would arrive after the crew had already made the earliest and most urgent decisions. Communication may become even less reliable during Mars solar conjunction. This occurs when Earth and Mars pass to opposite sides of our star, placing the brightest region of the solar system near the radio path between them. Charged gas around the Sun can interfere with signals, so mission teams may reduce commanding for roughly 2 weeks and allow spacecraft to follow previously uploaded instructions. A Mars crew would therefore need enough training, software, manuals, and local authority to continue through periods of delayed or limited contact. Mission control would remain valuable, though its role would resemble written consultation more than live supervision. Information can still cross the distance. Physical rescue must obey a much slower set of rules, determined by planetary motion, available propellant, and the spacecraft's existing path through space. A spacecraft traveling toward Mars is already moving sideways through the solar system at enormous speed. Earth circles the Sun at nearly 29.8 kilometers per second. Mars moves more slowly, at roughly 24.1 kilometers per second. A vehicle leaving Earth begins with Earth's orbital motion, then uses its engines to change that motion enough to enter a new path that intersects the future position of Mars. The destination is therefore a moving point. Mission planners must calculate where Mars will be months after launch and place the spacecraft on a trajectory that reaches the same region at the same time. The most efficient opportunities occur approximately every 26 months, or about 780 days. During each window, Earth and Mars reach a favorable arrangement for a transfer using a manageable amount of propellant. A common reference is the Hohmann transfer, an elliptical path connecting two roughly circular planetary orbits. A minimum energy Hohmann transfer from Earth's orbit to Mars takes about 8.5 months. Actual mission plans may use somewhat faster or slower routes, depending on available fuel, spacecraft mass, radiation exposure, life support limits, and arrival requirements. This geometry explains why turning around is more complicated than rotating the spacecraft. Small thrusters can point the vehicle in a new direction. Its existing momentum continues, carrying it along the original path, until an engine produces enough thrust to alter that motion. A spacecraft could face Earth while still traveling rapidly away from it. Engineers describe the ability to change velocity using the term delta V. Delta means change. So delta V is simply a measurement of how much a spacecraft can alter its speed and direction. Each departure burn, course correction, orbital insertion, landing maneuver, and return burn consumes part of the mission's available delta V. Propellant creates the change by being expelled from the engine at high speed. The spacecraft moves in the opposite direction. Once that material has been used, it cannot be recovered during the flight. Carrying additional propellant helps, though it creates a compounding mass problem. The launch vehicle must accelerate the fuel needed for later burns. That extra fuel requires larger tanks and stronger structure, adding still more weight. More launch propellant is then needed to accelerate the tanks, structure, and future propellant together. This relationship is described by the rocket equation. It places a severe cost on large velocity changes, especially when a spacecraft must carry everything from Earth. Mission plans therefore separate several forms of return. A planned return is built into the original architecture. The crew follows a prepared schedule, leaves Mars when the planets reach the required alignment, and uses a vehicle reserved for the journey home. An abort changes that plan after a failure. Depending on when the problem occurs, the crew might return toward Earth, continue toward Mars, enter a different orbit, or follow a long path through the inner solar system before reaching home. A rescue mission would require another spacecraft to launch after the emergency, follow the crew's trajectory, match its speed, and carry enough resources for the encounter and return. Catching a moving vehicle becomes increasingly difficult as the distance grows. Early in a Mars journey, some mission designs preserve abort paths that could eventually bring the crew back. Even these returns may take many months. Later in the flight, the spacecraft may have traveled far enough that continuing toward Mars uses less propellant than reversing course. System health matters as much as position. An intact propulsion system may still perform a major correction. A damaged engine, leaking tank, or failed navigation sensor can remove that option even when a return path exists mathematically. Planetary geometry also limits departure from Mars. Conjunction-class missions use relatively efficient trajectories and usually include a long stay near the planet, often around 500 days, while Earth and Mars move into position for the return. Including the outbound and inbound journeys, the complete expedition may last roughly 2.5 years. A crew experiencing a serious failure during that stay could remain unable to leave immediately. Their return vehicle might be healthy and fully fueled, yet the available trajectory could require more propellant than it carries. Earth would remain present in navigation displays and scheduled conversations. Its location could be calculated with great precision. Physical access would depend on engines, fuel, functioning hardware, and the current arrangement of the planets. Once rapid return disappears, the spacecraft becomes the crew's environment for months at a time. During every one of those months, radiation continues passing through the hull and adding to the dose already stored within the body. During a Mars journey, radiation exposure continues whether the crew is working, sleeping, or waiting for the planets to move into a better position. Two main sources shape that environment. The first comes from solar activity. Flares and eruptions can accelerate charged particles away from the sun at high speed. These events are often called solar particle events. Many of the particles are protons, and a strong event can raise radiation levels around a spacecraft within hours. The second source arrives from much farther away. Galactic cosmic rays enter the solar system from the wider galaxy. They include protons, helium nuclei, and heavier atomic nuclei that have lost all of their electrons. A nucleus without electrons carries a strong positive charge, allowing it to damage material as it passes through a spacecraft and through human tissue. Solar events arrive in bursts. Galactic cosmic rays form a nearly continuous background. NASA measured that background directly during the voyage of the Curiosity rover. Curiosity launched toward Mars in November of 2011 and traveled inside a protective cruise stage for about 8.5 months. Its radiation assessment detector recorded the particle environment throughout the trip. The average dose produced by galactic cosmic rays was approximately 1.8 millisieverts per day. A millisievert is a unit used to estimate the biological effect of ionizing radiation. It accounts for the amount of energy deposited in tissue, and for the fact that some forms of radiation cause more biological damage than others. Curiosity traveled during a relatively quiet period of solar activity. Solar particles contributed only about 3% of the measured cruise dose during that particular journey. A crew departing during different solar conditions could experience a different balance. The solar cycle lasts about 11 years. Near solar maximum, eruptions and particle storms become more common. The stronger solar magnetic field can also reduce part of the incoming galactic cosmic ray population. Near solar minimum, major solar storms are generally less frequent, while galactic cosmic ray exposure can rise. Mission planners therefore cannot select one season that removes both hazards. Solar particle events may allow some warning. Spacecraft near the sun can detect an eruption, and instruments can monitor changing radiation levels. A crew could move into a compact shelter positioned near the center of the vehicle. Water containers can be placed around that shelter. Food packages, equipment, and other supplies add more mass between the astronauts and the incoming particles. Materials rich in hydrogen are especially useful because hydrogen nuclei can slow many charged particles without producing as much secondary radiation as some heavier shielding materials. Galactic cosmic rays are harder to control. Their most energetic particles can penetrate thick layers of material. Some are heavy nuclei, traveling close to the speed of light. When one of these nuclei strikes aluminium or another shielding material, the collision can break the nucleus apart. The fragments continue through the spacecraft as a shower of smaller particles. This process is called nuclear fragmentation. The shield absorbs part of the original energy, while the collision creates additional radiation inside the vehicle. Adding more dense material can still provide protection, though the benefit depends on its composition, thickness, and the energy of the incoming particle. Radiation becomes harmful because it removes electrons from atoms and molecules inside the body. This process is called ionization. It can break chemical bonds, alter proteins, and damage DNA. Cells repair much of this damage successfully. Some damaged cells die and are replaced. Other changes may remain and increase the chance of cancer years later. Long exposure may also raise the risk of cataracts and cardiovascular disease. Researchers continue studying possible effects on the brain and central nervous system. Animal experiments have found changes after exposure to some high-energy particles, though the long-term cognitive risk to astronauts remains uncertain because very few people have experienced deep space radiation. Dose also changes with route and shielding. A crewed spacecraft may provide more protection than Curiosity's cruise stage. A faster journey would shorten the exposure period. A solar storm encountered at the wrong time could add a large dose over a much shorter interval. The danger therefore builds through accumulation. Most galactic cosmic rays pass through the spacecraft without creating a visible event. No cabin alarm sounds for each damaged molecule. The crew may feel healthy, while the total recorded by their dosimeters rises day after day. Radiation is only one process acting throughout the voyage. Even inside a perfectly shielded cabin, the absence of normal gravity would begin changing bones, muscles, circulation, and vision within the first weeks. Inside the spacecraft, the human body begins adjusting to an environment it has never encountered during its evolutionary history. On Earth, gravity places a constant load on the skeleton. Standing, walking, and climbing stairs all require bones to support weight while muscles pull against resistance. Bone tissue responds to those forces by continually rebuilding itself. In microgravity, much of that load disappears. The body begins removing mineral from bones that no longer seem to need their former strength. The greatest losses tend to occur in weight-bearing areas such as the hips, pelvis, and lower spine. Without effective countermeasures, astronauts can lose roughly 1% or more of their bone mineral density in some regions during each month of flight. Calcium released from bone enters the bloodstream and is later removed through the kidneys. This can raise the chance of developing kidney stones, which would be especially difficult to treat during a distant mission. Muscles change for a similar reason. The calves, thighs, back, and muscles that normally hold the body upright receive far less work. Muscle fibers shrink, strength declines, and endurance falls unless astronauts exercise intensively. Crews aboard the International Space Station usually spend around 2 hours each day exercising. A resistance machine uses vacuum cylinders to imitate the load of weights. Astronauts also run while held against a treadmill by straps and use a stationary cycle for cardiovascular training. These systems reduce the losses, though they do not reproduce every effect of gravity. Exercise equipment also occupies space, consumes power, and requires maintenance. A broken resistance machine on a multi-year voyage would become a medical problem long before the crew could replace it. Weightlessness changes the movement of fluid as well. On Earth, gravity pulls blood and other fluids toward the legs. In orbit, roughly 1 to 2 liters can shift toward the chest and head during the first days of flight. This creates the swollen face and thinner-looking legs, often seen in new astronauts. The body initially interprets the upper body fluid increase as excess volume and removes some water and salt. Blood volume can fall as a result. The pressure changes inside the head may also affect the eyes. Some astronauts develop a condition called spaceflight-associated neuroocular syndrome. Neuroocular refers to the connection between the nervous system and the eye. Observed changes can include flattening at the back of the eyeball, swelling around the optic nerve, and folds in the layer containing blood vessels behind the retina. Some astronauts experience changes in near vision that continue after returning to Earth. The exact cause remains under investigation, and individual susceptibility varies. The cardiovascular system also adapts. The heart no longer needs to pump blood upward from the legs against normal gravity. Over time, it becomes accustomed to a different pressure pattern and a lower circulating blood volume. When astronauts return to the ground, gravity suddenly pulls blood downward again. Some become dizzy when standing, because the body cannot immediately maintain enough blood flow to the brain. Reduced exercise capacity and faintness can continue during the first days of recovery. Balance is affected through the vestibular system inside the inner ear. Small organs there normally sense gravity and linear acceleration. In orbit, they receive no stable downward signal, while the eyes continue reporting movement and orientation. The brain gradually learns to interpret this unusual combination. Returning to gravity requires a second period of adaptation. Astronauts may feel unsteady, misjudge motion, or have difficulty walking normally after landing. A Mars crew would face an additional uncertainty. Gravity on the Moon is about 16.5% as strong as Earth's. Mars provides roughly 38%. Human beings have spent days on the lunar surface, but nobody has lived for months under lunar or Martian gravity. Researchers therefore do not know whether 38% of Earth gravity would preserve most bone and muscle, slow the losses, or merely produce a different form of decline. A rotating spacecraft could create artificial gravity. As the habitat spins, the floor pushes inward on the crew, producing a sensation similar to weight. A larger rotating radius can provide useful gravity with a slower and more comfortable rotation rate. A smaller habitat must spin faster, increasing dizziness and unusual sideways forces when someone moves inside it. Creating that rotating structure would add mass, bearings, seals, and mechanical complexity to the vehicle. NASA includes altered gravity among the central hazards of human exploration, because every long journey must preserve bodies designed for Earth. Doing so requires a complete artificial environment whose air, water, pressure, temperature, food supply, and waste systems remain active every hour of the mission. A spacecraft must continually rebuild the environment its crew uses up. Breathing removes oxygen from the cabin and replaces it with carbon dioxide, heat, and water vapor. Drinking moves stored water into the body before some of it returns through urine, sweat, and exhaled moisture. Cooking, washing, plant growth, and equipment cooling distribute the same limited supply through many different parts of the habitat. On Earth, these materials pass through oceans, soil, plants, weather systems, and treatment facilities. A spacecraft has to compress portions of that planetary cycle into machinery small enough to launch. Aboard the International Space Station, this work is handled by the Environmental Control and Life Support System. Its equipment regulates cabin pressure, removes carbon dioxide, produces oxygen, controls humidity, processes wastewater, and filters trace chemicals released by people and equipment. Moisture from an astronaut's breath and skin condenses inside the station's ventilation system. Instead of allowing that water to collect on walls or disappear into waste storage, the system captures it as humidity condensate and sends it for treatment. Urine follows a separate path through the urine processor assembly. The liquid is heated under reduced pressure, allowing much of the water to evaporate at a lower temperature. That vapor is separated from concentrated waste and condensed again. The remaining brine still contains usable water. Brine is the highly concentrated liquid left after most of the easier water has been removed. For many years, part of that moisture could not be recovered efficiently aboard the station. A newer brine processor assembly improved the process. It uses special membranes and warm, dry air to pull additional water from the leftover brine. After this upgrade, NASA demonstrated total water recovery approaching 98%. The recovered liquid then enters the water processor assembly. Filters remove particles and dissolved contaminants. A catalytic reactor uses heat and oxygen to break down small organic chemicals that remain. Sensors examine the finished water before it returns to storage for drinking, food preparation, and oxygen production. A recovery rate near 98% is a major engineering achievement. It also means that roughly 2 units remain unavailable for every 100 units passing through the complete cycle. On a 6-month station expedition, losses can be replaced by stored reserves and later cargo deliveries. During a voyage lasting several years, the same small percentage compounds. A multi-generational vessel could not depend on regular tanks of replacement water arriving from Earth. Some losses occur because water remains trapped in filters, concentrated waste, food packaging, plant tissue, cleaning materials, or inaccessible chemical compounds. Maintenance can spill small amounts. Airlock operations may release humid cabin air into space. Each loss is minor by itself, though a closed habitat must account for all of them over time. Oxygen also moves through a cycle. The station can split purified water through electrolysis, a process that passes electricity through water molecules and separates them into hydrogen and oxygen. The oxygen enters the cabin atmosphere. The hydrogen can be combined with carbon dioxide removed from the crew's air. Inside a Sabatier reactor, these gases produce water and methane. The water returns to the life support system, recovering part of the oxygen and hydrogen that would otherwise be lost. Methane is generally discarded because extracting its hydrogen requires additional equipment and energy. Each stage depends on physical hardware. Membranes can become coated with contaminants. Catalysts slowly lose effectiveness. Pumps wear as internal surfaces move against one another. Filters collect material until airflow or water flow becomes restricted. Sensors may drift, meaning their readings gradually become less accurate even though the instrument continues operating. A recycling percentage therefore describes the performance of an entire chain rather than a permanent property of the spacecraft. The loop remains nearly closed only while every important link stays powered, calibrated, cleaned, and repaired. Food presents an even harder problem. Water molecules can be purified repeatedly without changing their basic identity. A complete food cycle would need to recover carbon, nitrogen, phosphorus, and other nutrients from human waste and dead plant material, then return them safely to new crops. Plants would also require light, growing space, temperature control, pollination, and protection from disease. A failed crop could remove both food and part of the system used to refresh the air. Deep space survival depends on reclaiming the same limited material many times. The crew may recognize the water in a drinking pouch, while its earlier forms could have included cabin humidity, wastewater, or moisture recovered from concentrated brine. When part of that cycle fails, the problem quickly crosses from engineering into medicine. Far from Earth, the people who diagnose the crew and the people who repair the habitat must already be aboard. A closed habitat can recycle air and water, yet it cannot guarantee that every person inside will remain healthy. Astronauts assigned to the International Space Station undergo extensive medical screening before launch. Doctors look for conditions that could become dangerous in orbit, including heart problems, unstable vision, kidney stones, and dental disease. The goal is to reduce the chance that a hidden problem will appear during the mission. Once aboard, the crew has medical kits containing medications, bandages, intravenous supplies, emergency equipment, and tools for examining injuries or illness. At least 2 crew members usually receive additional medical training, even when neither is a physician. Flight surgeons on Earth can speak with them almost immediately. These doctors review symptoms, vital signs, images, and test results, while specialists from other fields can join the consultation when needed. Ultrasound has become especially useful in orbit because a large X-ray or magnetic resonance scanner cannot be carried easily aboard the station. An astronaut can place a handheld ultrasound probe against the body while a doctor on Earth watches the images and provides guidance. Crews have used this method to examine muscles, blood vessels, internal organs, and possible injuries. A serious case still has access to evacuation. A docked return vehicle can carry the patient back through the atmosphere, where ambulances, hospitals, operating rooms, and specialist teams are waiting. That medical structure changes during a Mars mission. At the greatest communication delays, a crew member could report severe abdominal pain and wait more than 20 minutes for the message to reach Earth. A doctor might study the information immediately, yet their response would require another 20 minutes to return. By then, the patient's blood pressure, pain, or level of consciousness could have changed. Some conditions allow time for consultation. Others demand action within minutes. A severe allergic reaction may obstruct breathing. Internal bleeding can continue without producing an obvious wound. A burn inside the habitat may involve damaged tissue along with smoke inhalation. A fractured bone could threaten nearby blood vessels or prevent a crew member from performing essential work. Kidney stones are especially relevant because bone loss in microgravity can release calcium into the bloodstream and urine. A small stone may pass on its own. A blocked urinary tract can cause intense pain, infection, and kidney damage. Dental problems create a different challenge. A cracked tooth or deep infection may require drainage, extraction, pain control, and antibiotics. On Earth, a dentist can take detailed images, sterilize instruments, choose among several treatments, and arrange further care. A distant crew would work with a limited set of tools and whatever training had been completed before launch. Appendicitis is often used in exploration planning because treatment may require surgery. Performing an operation inside a spacecraft involves anesthesia, sterile equipment, reliable monitoring, trained assistants, and a safe recovery area. Blood for transfusion is difficult to store for long periods, while the crew may be too small to provide a compatible donor without creating another medical risk. Terrestrial medicine remains dependable, partly because it is spread across many layers. A local clinic can send samples to a laboratory. A hospital can call a surgeon, cardiologist, or infectious disease specialist. Pharmacies and blood banks replace supplies as they are used.